In this tutorial, we'll be discussing chemical reactions and chemical equations. So let's talk about things that you've actually experienced in the past. Alright, so you've possibly seen a shuttle take off on TV. What happens is the red molecules here are actually hydrogen molecules, and the oxygen molecules here are both stored inside this big red tower. And then as these combine, they explode to make water. Another example that you might be even more familiar with is when you're driving your car. You fill your car full of gasoline, which is octane. In the engine, it combusts. It reacts with oxygen. And then out the tailpipe comes carbon dioxide and water. So if we could actually see what's going on in the molecules that compose the matter, we could see how the chemicals are changing from one to the other. So atoms with other atoms are combining with other atoms to form compounds. Or they're forming new molecules in the process. They decompose. Or they change places. Those are just some examples of different ways things can react. The bottom line is what's there at the beginning is going to rearrange itself to be something new at the end. All the atoms are staying there, but the fact that they're rearranging is what's making it a chemical reaction. If we could see the atoms and molecules that compose the matter, we can know that there's a chemical reaction. But of course, they're so small we can't actually do that. So we have to have some other way of identifying a chemical reaction. And that's where we get the evidence of the chemical reaction. So over here, you'll see the summary of the different ways that you can tell that there's a chemical reaction going on. The first one is a color change. So for instance here, you may have experienced this if you're working with young children. If you put a temperature sensitive spoon into something hot, it'll change colors. And that color change is because the molecules inside here are rearranging with the heat. And then once you take it out of that color, it goes back to the way it was. Another evidence is formation of a precipitate. That's a solid. So if you see a solid form in the solution, that's another example of an evidence of chemical reaction. Another one would be it forms a gas. So here's an Alka-Seltzer here. You may have also seen other things that give off gas when you drop it into water. But the fact that the gas is being given off is another evidence of a chemical reaction. The evidence also relates to heat and light. The absorption or emission of light, which is here, is an example of evidence. While the burning or taking in cold, something getting colder, heat absorption or giving off, is another example. So don't be fooled though. Not every time something gives off a gas, it doesn't obviously means it's not a chemical reaction. For instance, if you boil water on your stove, that's not a chemical reaction. That's actually a physical change. What's happening is the heat from the flame is heating up the water, and those molecules are expanding and going from a liquid to a gas. And as they're expanding, it's becoming less dense, and then it rises to the top. So when it pops up here, this boiling is actually still water. It's just water vapor. It's water gas. So don't be fooled. Just because it gets a gas doesn't mean it's a chemical reaction. You have to look at everything that's going into it. Alright, so changes occurring in atomic and molecular level determine whether a chemical reaction has occurred. Only true chemical analysis shows that the initial substances have changed from what it was before to what it is after. It can occur without any obvious signs, but that evidence that we just talked about is a way of double checking. So when you're trying to ask yourself if something's a chemical reaction, which chances are your instructor will have you do this, I want you to think of two questions. One, is it the same thing as when you started? Two, can you easily change it back? That's what I want you to think about. So, for instance, tearing paper. If you rip a piece of paper in two, is it still the same thing? The answer is yes. They're two pieces of paper, but they're still paper. If you take that paper and you set it on fire and you burn it, is it still the same thing? No. It's now ash. It has a different name. It looks completely different. You cannot turn it back very easily. Frying an egg. Can you unfry an egg? It's still an egg, but can you unfry it? The answer is no. Since you cannot change it back to the raw state, it's a chemical change. Melting glass. You can solidify the glass afterwards. So since it's easily changed back, that's a physical change, not a chemical. So let's go through this again. Tearing paper is physical because it's still paper. Burning paper is chemical because of the fact that it's now considered ash. You can't change it back to paper. Frying an egg, you cannot unfry an egg, so that's chemical. Melting glass is physical because you can easily change it back to a solid piece of glass. So we represent chemical reactions with chemical equations. And the substances on the left are the reactants, and on the right you have a product. And in between the two, you have an arrow saying this is going to that. And then you might see some little letters next to it in parentheses. That is the physical state of each reaction. So here's a visual of what I'm talking about. We have methane, CH4, reacting with oxygen to produce CO2 and H2O. On the left-hand side is our starting point. It's just like reading a book. You go from left to right. So on the left-hand side is your starting point. That's your reactants. On the right-hand side is your products. That's what you end up with. The arrow separates them, saying that this, the left side, is becoming the right side. You might see this in words by saying to form, produce. Those are the two main ones. But there are other ways to use that word for an arrow. So CH4 and O2 react to produce, and that's that arrow, CO2 and H2O. Now notice these little letters here. That's what it's referring to. These are subscripts. And they're referring to the physical state. So CH4 is a gas. So it has a G next to it. If it was a liquid, like if the water produces a liquid water, it would have an L there instead. AQ means it's been dissolved in water. It's aqueous. So let's take this a little bit further and look at the atoms from left to right. So we have C, H, and O on the left-hand side. We should have C, H, and O on the right-hand side too. Things don't just disappear or be created. They come from one side to the other. So if you have C, H, and O, you should have C, H, and O on the right-hand side. Now I want to take another look. On the left-hand side, we have two oxygens. On the right-hand side, we have two oxygens here and one here. We have three oxygens. The ones on the left have to be the same as the right. Things don't just disappear and reappear. Let's look at the hydrogens. We have 4 hydrogens on the right, or on the left, pardon. On the left because of the CH4. We only have 2 hydrogens on the right because of the H2O. Once again, we have to rectify this. We have to correct this. We do this through balanced equations. So, in order to do that, we put numbers in front, and these are called the coefficients. You do not insert numbers into the equation, into the chemical formula. Once that chemical formula is set, you need to leave it alone. Only thing you can do is use the coefficients in front to multiply that. So what that's saying is I have 2 times 2 hydrogens, and I have 2 times 1 oxygens. Here, this means I have 2 times 2 oxygen, so I have a total of 4 oxygens. The number in front multiplies it just like it was in algebra class. So here we have, look at the left versus the right. We have one carbon all in the left-hand side. Over here we have one carbon. On the left-hand side for hydrogens, we have 4 here. On the right-hand side, we now have 2 times 2 to equal 4 hydrogens on the right. Oxygens, we have 2 times 2 for 4 oxygens. And 2 oxygens here and 2 times 1 here. So 2 plus 2 is 4. We're going to go into this in a lot more detail in another tutorial, and it will take us through step by step how to balance equations. The numbers of each type of atom on both sides of the equation are equal and balanced. That means that the equation is balanced, and that's good. That follows the law of conservation of mass. A balanced chemical equation represents a chemical reaction. So this is the final product. Once again, in another tutorial coming up, you'll see how to balance equations very slowly, and we're going to go through a lot of practice problems.